All right, welcome to the How to Write an Interpreted Programming Language crash course for HacKnight. We're going to do introductions first, even though you already did them. Everybody just go around and say your names.
Say your name and what coding language you're most proficient in, or most comfortable with, or have most experience with.
Or like the most.
Or like the most. I'll start. I'm Paul. I'm a junior here at BB&N, and I'm one of your workshop organizers today, along with Ethan. And I'm most proficient in Java due to having taken the APCS course, but there you
go. I'm Ethan. I'm also an organizer today. And I think I like Python the most, just because it's easy.
I'm Adrian. I took APCS for 2 weeks before dropping out, so Java.
Excellent.
I'm Alec, and I think Scratch is just kind of fun to mess around with.
I'm Alex. I like JavaScript, TypeScript.
I'm Oliver. I'm probably most proficient with Python, but I like other languages too.
Cool, great. Now we're going to do a topic overview and just discuss like what is a programming language, and more importantly, like what is an interpreted programming language. What are you guys actually learning how to do today and trying to do today? So what actually is a programming language? Paul, what do you think?
Well, I would say...
Okay, your job has been replaced by AI. A programming language is a formal set of instructions that can be used to produce various kinds of output, allowing humans to communicate with computers to perform specific tasks or solve problems. So it can be pretty much a range of just ways to interface with a computer, to give it instructions, and to get something done. There are two main types of programming languages. So compiled programming languages and interpreted programming languages. And the biggest difference is just how it takes what we've written and gets it to something that the computer can understand. So in compiled programming languages, it's translating that code into machine code. So that's like your ARM assemblies or etc. And what it does is it compiles it, and then it has this executable program that's really easy for the computer to understand, and it gives it to it all at once, and it goes through and executes it. So the major pros of that is that you've compiled it, so now you have this file that's really fast to execute, and that you can optimize really well for the machine that you're trying to run it on. The major cons are that you have a longer development cycle. You can have platform dependency, where you've now written it to compile into this machine code, and it does that better on one machine versus another, and it's not very versatile in that respect. And then also they just tend to be lower level languages, because if you're compiling directly into machine code, that's a harder thing to do than to interpret, and that's partially why we chose in this relatively short session today to explain a broad topic to teach you how to write an interpreted language. What is an interpreted language? Well, interpreted programming languages execute code directly line by line, and that is after interpreting it into another, like more machine readable piece of code, and executing that line. So the biggest difference that people will tell you between a compiled language and an interpreted language is that a compiled language gets compiled to an executable, you run that big executable file. An interpreted language, you go line by line and you interpret a line of code into another more readable line of code and execute it, and yeah, and that's how that works.
So on and so forth.
But the simplest version of writing an interpreted language is really just going to be taking a set of text where you want the syntax to look one way and converting that into a language, into another pre-existing language. So that's like, think your Python that gets interpreted into C. And the major pros of that are that you have more flexibility for runtime changes because it's executing line by line. It's easier to debug just because when we'll get into this later, you split the code up into tokens, then you parse those tokens, and you can do some runtime syntax assessments there. And then the major cons are you have this line by line step of interpreting one piece of text into another, and that's going to mean that you have slower execution speed, and that's going to mean that your computer memory is more occupied in the process of executing the program.
Does anyone have any questions? Does that all kind of make sense?
Yeah.
Okay, good.
we'll get like more
You'll get more familiar with it as
in depth, and you also don't to do it. You don't necessarily have to understand like all the nitty gritty elements. So this is sort of just what I was just explaining, but it's more. This is a flowchart. It's more visual. So the compiler, you have your source code. So that's the code in your preferred language. So like C, for example, and it's the compiler takes it and outputs machine code, and the machine code is executed for the output versus source code going into an interpreter, which gives you, a line by line output. And we have a video to give you a bit more context because I cannot always do the best.
So we need to get our source code converted into machine code somehow before it can run. And there are two main ways of doing this. What's called compiling the source code and what's called interpreting the source code. Now luckily this is not a big decision you have to worry about. Most languages you'll deal with will naturally fall into one or the other, but it is worth knowing the difference. So let's have a simple scenario. Let's say it's just you and me. You have your computer and I have my computer, and you're going to write a program that you want me to run. Now with a compiled language, what happens is you write your source code, and then you have a program called a compiler that will go through that source code and create a separate file that contains the machine code. And you just give me that file. This end result is sometimes referred to as an executable or an executable file because I can directly execute it. I can now just run your program. You keep your source code and I never see it. Now with an interpreted language on the other hand, you don't compile your source code beforehand. You just give me a copy of it. So I'll need my machine to interpret it whenever I want to run your program. Now an interpreter is different to a compiler. It does this on the fly. We can think of it as going through your source code line by line and processing it on the spot. It does not save it as a separate machine code file. Now you've used interpreted languages even if you don't know it. Whenever you've looked at a web page with JavaScript, which if you've surfed the web for more than 2 minutes in your lifetime, you have, this is what's been happening. The JavaScript has been sent to you over the web along with a bunch of other files like web pages and images, and it's been sent as source code onto your machine, and your web browser has just interpreted that JavaScript so it can run that code. So which one's best? Well, they both have their good and their bad points. Benefits of compiled code. Once it's compiled, it's immediately ready to run, and you could send it to 100 or 1,000 or 100,000 different people. It's ready to go. It can be optimized for a CPU, so it can actually be faster. And you don't have to send your source code to everybody, which might be a good thing. However, the downsides are if I compile it on a PC, that executable file won't work on a Mac. In fact, it often needs to be compiled separately for different kinds of CPU, even on the same platform. And when you're writing code, to compile is an extra step that you have to take every time you want to test your program. Now with interpreted code, the big benefits are I don't really care what kind of machine is on the other end, because we don't provide machine code. We just send the source code and we let the other side take care of it. So it can be more portable and more flexible across platforms. It's also a little easier when testing because you just write your source code and then run it, letting the interpreter take care of converting it. There is no in-between compile step. And it can be easier to debug when things go wrong because you always have access to all the source code. However, it has its downsides too, because everyone who needs to run that program on their machine has to have an interpreter for that language on their machine. It also can be slower because you have to interpret it every time the program is run. And the source code is effectively public because you're sending it to everyone who needs to run that program. Now, because there are good things about compiled languages and good things about interpreted languages, there's also a third way of doing this, which is a bit of both. Instead of the compile model where all the work is done up front but can be a little bit inflexible, or the interpreted model where all the work is done on the receiving end but can be a little bit slower, we kind of do half and half. Up front, we compile it part of the way to what's called an intermediate language. which takes it as far along the way to machine code as it can get while still being portable, often across platforms. You then distribute this, sending it to the people who need to run it, and each person who runs it takes it the last step to take it to machine code on their computers. This is sometimes referred to as just-in-time or JIT compilation. Now this intermediate language sometimes also goes by the name of bytecode. So this process has to happen somehow. It's just how much of it happens on your machine and how much of it happens on mine. Now, while theoretically all computer languages could use any of these methods, the normal usage of any one language tends to be one or the other. So for example, C, C++, and Objective-C, these are typically found as compiled languages, so you need a compiler. And the compiler can be downloaded for free, but are often built into integrated development environment applications. Now, languages like PHP and JavaScript, indeed most languages with the word script at the end, are usually interpreted. And languages like Java, C#, VB.NET, and Python use this intermediate hybrid approach. Now, whether a language is compiled or interpreted, or somewhere in between, is rarely a reason by itself to choose a language, but it can be something that you take into account. If one main priority of your program is absolute maximum speed running on one single platform, you'll probably look at a compiled language. If you're more interested in easily moving your code across multiple platforms, you're probably more interested in an interpreted one. But more usually, you're driven more by what you need to do. Do you need to build iPhone apps or Windows desktop apps or dynamic websites, or in our case, just learn the fundamentals of programming? And you let that decision drive the language choice, and the language choice will determine whether you're compiled, interpreted, or somewhere in the middle.
Okay. So what we hadn't covered before was that like hybrid model, which is sort of what you see here, where there's still like a step. There's not just it's interpreted and then it goes to output. There's the step of compiling it into something that's easier, and then the Python virtual machine is that, like on your end, takes it to the final step of machine code. And then I also have just another like more in-depth look at like compiler language C, where you see that it's goes through an assembly code, goes through a compiler to assembly code. An assembler takes that and actually gives you like an object file. You guys won't need to know this for today. And then it has to. There's still more steps. Is all I'm saying. It is a more like complicated and nuanced process, especially when you're trying to get that to work for a range of different hardware. All right, so we were originally going to have you guys all use C and interpret things into C. We changed our model a bit, but there are a few reasons. Like if you are making an interpreter that goes language to language, you're probably going to choose a language that is more low level and has all the efficiency advantages and other things of a compiled language. Just because you already have the interpretation step, you don't want to like further bog down by being like you interpret your language into Python. However, that's what a boring person would say. Today, you can do whatever you want. If you want to take a bunch of text and turn that into JavaScript or Python, which then gets turned into another file through another interpreter, we do not care. Nope. You can do that. You can make the syntax as weird and funny as you want.
Yes.
All right, that was a lot of talking. I don't like talking. Guys, you can get out your computers. We're gonna do a Kahoot.
Let's go. Alex, we're gonna make it so it's through 18 languages.
So it's like, wait,
Sure. Yeah.
for like, we're turning our code to a polyglot.
Could this be used for making code secure? Like it has to run through a bunch of different languages?
Well, if you want, if you don't want like everybody to have the source code
Yeah.
to execute it, then you do want a language that's going to go that's going to just be an executable and not be the source code, because it's just harder to look at that way. But having a language that's interpreted a bunch of times over, probably not. No, that probably just makes it more annoying for you.
Yeah.
Isn't switching code from one language to another transpiling, not interpreting?
Transpiling. Well, it's not interpreting. It's also not like.
Wait, is this like on the fly, or does it like take like the file and then turn it into another file in a different language?
It's on the fly.
Oh,
Yeah,
okay.
that's what it's line by line. Yeah.
What's the Wi-Fi?
Wi-Fi is
Do you have your-
BB&N students. Your password is somewhere.
Yeah, that's like the most important thing is that it's like that's the biggest defining trait of an interpreted language.
Oh wow,
It's not
who has
like
changed since I
creating
played
a-
it?
Password blue for gold.
Not like a
No.
I just have such a cool screen
Okay, rolling. Alright.
Is like the Coop game?
Here we go, guys. You got it, guys.
Oh,
Wow.
nice.
Wow.
I'm on the podium. Not
That's
the brag.
right.
We're all on the podium.
Odds. Surely. Yeah.
Well, I was close.
Because some.
Yeah, not the brag, but I'm on the podium.
I thought I was getting.
I'm a runner-up.
But I'm on the podium.
Yeah, I'm a runner-up. That's pretty good.
You're not even runner-up.
I am. I'm in fourth.
Oh.
Major pro, higher memory usage.
That is a plus. I won my computer explorer.
Well,
Brilliant, brilliant, brilliant.
it was 2 weeks of comp sci did not serve me well. Let's go.
I'm gonna lead by 40 points.
Big 40 point.
Yes, it lacks portability. Very.
That was a badly written question.
C is most definitely
Compile
not
it.
an easy language to just pick up.
I wrote this question wrong.
Oh,
You don't compile into a language. That's my
Oh,
bad,
yeah.
guys.
I would have gotten it right if it wasn't for that.
No, I'm still on the podium.
there you go. Good. All right.
Place, baby.
4th place. Hey, you made it.
I almost
top
got
3.
I almost top 4.
Yeah, top 4.
Almost got a medal.
What can I say?
Okay.
Yeah,
Guys
I'm a
have been
lifelong
thoroughly
learner.
Introduced to the subject.
Are you a Sigma learner?
Don't. Don't. Says I'm a lifelong learner. That's pretty good. Pretty good.
Okay. A few more slides and then we're gonna let you guys
It's
loose.
been literally 6 years
All
since
right.
I last played a game.
So, we've introduced what we're doing. We're writing an interpreter, but interpreters need to be broken down further into
Yes.
to more things that we can understand how to do if we want to actually write them. And what we're going to break them down into right now is lexers and lexer and parser. So parsers are by far more complicated, and you also need a lexer before a parser. So I'm going to explain what lexers are first. It's taking your source code as input, and what it's going to do is it's going to break down this input into a bunch of different tokens. So it's taking the characters, it's taking like your if, and it's saying like this is a token that has value and that we're going to need to look at as an operator in the program. And then it's going to generate a list of those tokens and identify, like what's an operator, what's an identifier. It's going to identify that white space means nothing and that it's just for our readability. And then it might have like handlers for specific tokens. So that's basically it. That's basically all we need to worry about for lexers. And I'm trying to think. I think we'll look at parsers first, and then we'll write one as a group.
Yep.
So parsers are going to look at those tokens, and what they're going to do is they're going to analyze the structure of tokens based on some predefined written rules, and then it's going to generate a tree for how it's called an abstract syntax tree, and that's basically just how are we going to look at and execute this set of tokens. So the reason that we do this is because this is going to give like a structure for, you need, if you just have a bunch of tokens, there's no link or order to what goes into getting the final result. So that also means that you can detect syntax errors when you look at some tokens and it doesn't make sense, you're missing parentheses, et cetera, et cetera. Abstract syntax trees, there's a bit more to it, and we're going to watch some videos on that, and then we'll do a few activities to understand them better. So that's what we're moving into now.
ST. At a high level, an abstract syntax tree is an intermediate representation of source code as a tree structure. But what does that actually mean? Let's break each part of the statement down. To start, let's look at the tree data structure. A tree data structure starts with a root node. The root can then point to other values, and those values to others, and so on. This begins to create an implicit hierarchy, and also happens to be a great way to represent source code in a way computers can easily interpret. Each one of these values, or circles in the tree, are referred to as nodes. The relationships between nodes are often described with terms like child node, parent node, sibling node, and so on. By convention, the root node is shown at the top. However, if it's flipped, with the root node at the bottom and the rest of the tree heading upwards, it starts to look like an actual tree, with all its branches forking out. Tree data structures are common in computer science and have many practical applications, such as searching and sorting data. There are also many different types of trees with different constraints. For example, a binary tree is a tree with at most 2 child nodes. For the purpose of working with ASTs, the important aspect is understanding how a tree can be used to represent data in the relationships between nodes. Some of the most prominent uses of ASTs are in compilers. A compiler accepts source code as input and then outputs another language. This is often from a high-level programming language to something low-level, like machine code. In the front-end web ecosystem, this includes tools like Webpack or Parcel. These tools compile many modules into a bundle and perform other optimizations such as transpiling from modern JavaScript to an older version, or minifying the code by renaming variables and functions to shorter names. Although they are a little different to conventional compilers, they follow many of the same fundamental steps. Compilers are commonly broken down into 2 parts, the front-end and back-end. The front-end is responsible for scanning and parsing the source code, while the back-end is responsible for producing the output. One benefit of making this distinction is the ability to
And again,
What is an AST?
Don't get, we really don't care too much about a lot of that because we already know our application, which is for an interpreter, not a compiler. But
Or transforming These include counting how many times a function, variable, component, or prop is used in source code, or transforming code from one syntax to another, or enforcing rules for syntax or other static analysis, for example, disallowing unused variables. Once familiar with abstract syntax trees, many of these concepts can be carried from one tool to another, as they will be built on many of the same fundamentals. Now that we have a base understanding of what ASTs are and how they work, what does a basic AST look like in practice? Let's take the following line of JavaScript as an example input. This code can then be represented by the following abstract syntax tree on the right. You'll notice there's a single root node. Here, that's the addition operator. In practice, the root node represents the entire file, but for the purpose of this example, unnecessary nodes have been omitted. Each child node, for example the numeric literal 2, has one unique parent. This can be said for all other nodes in the tree except the root. Finally, the tree structure implies hierarchy, which means syntax such as parentheses can be omitted. For example, to evaluate this tree, the multiplication must occur before the addition. Looking at a visual AST like this can be a helpful way to understand the structure. However, this isn't the true representation of what an AST will be when working with it in later lessons. A more common format is to represent this abstract syntax tree in the JSON format. Using the same example code, a simplified JSON structure representing the AST can be seen on the right. Most tooling that relies on ASTs operate on a JSON structure like this. As the tree becomes larger and more complex, it can become harder to visualize the structure. Take a moment to relate the visual representation and this JSON format of the same tree. Visualizing source code in a tree structure like this is one technique that can be helpful when reasoning about ASTs. Here, the entire statement is considered a binary expression node with three primary properties: left, operator, and right. The left node is then a numeric literal node representing the value 2. The right node, however, is yet another binary expression node, again with the properties left, operator, and right. However, this time, this nested binary expression's left and right nodes are both numeric literals, representing the values 4 and 10.
If you want to keep learning about how...
Okay, so that's kind of, that's the basics of lectures and parsers. We're gonna do another review, and then we're gonna look at what any of this actually means when you're trying to program.
Does anyone have any? Does everyone somewhat understand what's going on with that?
Yeah. Any questions?
Yeah. If anyone has any questions at any time, just shout them out.
Are we gonna actually make JSON files like that, or is it just kind of like that? Or we're gonna make like actual trees?
That is.
You have a marker.
Take one over there.
No, we're not. But that's more because that's just purely a data representation. So our programs are gonna sort of group things like that, but we're not really gonna see anything like that.
Look at this silly little guy.
Ready? All right.
That's literally not you. Wait, what? What happened?
Okay, this is the intro. My bad, guys.
What?
My bad. Whoops.
What are you doing?
This is the wrong quiz.
Go back.
Those are the questions. Those aren't quizzes, those are questions.
Oh no, you guys are answer too.
Oh, yeah, I see.
Like, can I get?
Guys, I'm a bit
But I don't got a computer though.
Okay.
I actually left my
Lectures and
backpack in.
parsers.
I'm not really sure which one.
Alright, never mind. Take two.
what are you teaching?
How to write a programming language.
Ooh, that's actually really
I don't want to be
interesting.
a job coach.
So we're just doing
Where's the
fundamentals
skills
right now.
Yep. Uh-huh.
This is our lectures and parsing scheme.
Yeah.
We're short one though. I don't know if
I
they
feel like they added cosmetics to good.
We're short one person.
There's a group that's short 4 people and they don't have anyone there. And they have 3 people teaching it.
Oh my god.
Who is it? Which activity was that?
Wow.
It's the stocks one.
Wait. That's what I want to do.
Yeah, you're doing it in the next. If you want to do it in the next one, that's really good actually.
Dang.
Yeah.
Come on. No! No!
5 points.
Wait,
I
what?
don't know if I told you guys this, so good luck.
I'm just gonna take a guess. Yo, you.
Yep.
It's called a lexical analyzer. So syntax
If you only copy my answers, you'll live in my shadow.
That's okay.
Wait, Ethan, have you guys made a coding language?
like very basic.
Yeah.
Basic one.
Awesome.
I'm just gonna guess the long one.
Bro, Adrian, move. Go back to the seat.
No!
Oliver takes the lead.
Actually,
3 points! Wait, what?
Is it orange every time?
Nice. We don't care about white space.
Orang.
I guess you could write a language.
2
that was,
points.
like just in negative space.
Ooh,
That would be a lot.
Oliver, you're falling behind, buddy.
Mine's too slow.
It's orange every
Come on,
time.
come on.
I'm just gonna click orange on the next one. Oh, it's over.
Alex lead.
Come on. Oh no, no, I clicked
No!
It's over. It's over.
How? How did both of you screw that up?
Tokens.
I just saw the word.
That was good.
I just spammed
It's over.
orange.
I'm still in second.
How? I just clicked orange.
I don't know if I told you this.
I don't think we did talk about this.
Yeah, it's always a long
There you
one.
go.
Let's go. I'm on the podium. Are you proud of me?
Yes, of course.
Okay.
Ethan, are you proud of me?
Yes.
We're all so proud of you.
Thank you. That's all.
Can you go back to your seat now?
Oh. It says I'm simply a prodigy.
It's true.